So this video is going to be an introduction to bonding, to how atoms come together to make a molecule. And this whole concept of bonding is all based on something called the Octet Rule, which is what this whole video is going to be about, although I'm not going to define Octet Rule until pretty much the end of the video, because there's a lot of introductory stuff that we have to get to before we can define it. Basically, in this video, we're going to be talking about how two atoms come together and interact with each other to connect and make a bond so that they're linked together and can become part of a molecule. In the last video, when we were talking about the structure of the atom, I talked with you about the electrons being outside in the electron cloud, and talked about how some of the electrons, called valence electrons, were given or allowed to have the largest area of space around the nucleus of the atom. So the valence electrons were the ones that had the biggest region of space that they could occupy, and they were the ones that were allowed to get really far away from the nucleus, further than any other ones. And I said towards the end of the video that the valence electrons, the ones on the outside of the atom, were the ones that interacted with each other when two atoms came together to make a molecule. So the valence electrons that are sitting on the outside surface of the atom, when the two atoms come together, it's actually the valence electrons that interact with each other and form the connection between the two atoms to make a bond. So just as a reminder, the valence electrons we're calling the outermost electrons because they are on the outside of the surface of the atom, and they are the electrons that are used to form a bond to another atom. And the bond is exactly what you think it is. It's just a connection that holds the two atoms together. So what we need to be able to do is figure out how the valence electrons interact with each other to form bonds, and that will enable us to predict how atoms are going to interact with each other and also how molecules are going to interact with each other. And one of the most important pieces of information that we need to have before we can make any kind of prediction about interaction is the number of valence electrons that an atom has. Because it turns out that the number of valence electrons in an atom is a huge predictor in determining how it's going to interact with another atom. So it's the first thing that we need to figure out. In the last video, we talked about how we can predict the total number of electrons in an atom by looking at the periodic table. So we said, I think the example we used was boron. We said the atomic number of boron is 5. No, we didn't use boron, we used lithium. The atomic number of lithium is 3, which means that lithium has 3 protons, and it means it has 3 electrons. But that just means it has 3 electrons total. That doesn't tell us how many of those electrons are valence, how many of those electrons are hidden on the inside of the atom. So the atomic number just gives us the total number of electrons, not the valence number. However, the valence number for each atom is given on the periodic table, just like the total number of electrons, and it's really easy to find. If we want to know the number of valence electrons in our atom lithium, all we have to do is find it on the periodic table, which we already did, see what column it's in, which we've already done, go up to the top of the column and find the number that's connected to the letter. The number, in this case the letter A, the number tells us how many valence electrons there are. So lithium, because it's in column 1A, has 1 valence electron, and it's as easy as that. So all you have to do is find the atom on the periodic table, find the column number, and all the columns actually have 2 numbers. You want to find the column number that has the letter A after it, and the number the column number, is the number of valence electrons. So, for example, silicon, Si, it is in column 4A, so that means it has 4 valence electrons. All the atoms in this column, column 6A, have 6 valence electrons. All the atoms in this column, 3A, have 3 valence electrons. It's as easy as that. You will also, as I said before, you'll notice that every column has 2 numbers on it. There's 1, 2, 3 all the way across to 18. Ignore those numbers. They don't give us any information about the number of valence electrons. You'll also notice that some of the atoms, or some of the columns, have the letter B instead of the letter A. We don't work with any of these atoms at all in this class, so you don't even have to worry about what's going on down here. All the atoms that we work with are in A columns, no problem. There's only one exception to this whole rule, the column number is valence number, and that is for the atom helium. Helium is in column A, and all of the atoms in this particular column have 8 valence electrons, except for helium. Helium has only 2. It is the one exception that you have to learn. Helium can't have 8 valence electrons. Its atomic number is 2. It only has 2 electrons total. So it's not even possible for it to have 8 valence. So what we're going to do next is practice finding valence electrons for a few different atoms on the periodic table, and then we're going to start putting this together to figure out how we can predict bonding for an atom. We're going to make a little table here we are going to do carbon, nitrogen, hydrogen, oxygen, and chlorine. I left a lot of room over there. Actually, I changed my mind. I'm going to make this into 2 columns. We'll do chlorine, and we're going to do neon. And in this table, we are going to make a count of the number of valence electrons that each of these atoms has. And we are going to draw something called the Lewis dot symbol, which is a picture representation of the valence electrons in the atom. It's a visual thing that we use to help us predict bondings. Chemists are very visual. And we are also going to predict how many bonds each of these atoms wants to make. Okay, so we're going to start with the stuff that you already know how to do. The number of valence electrons. So all we have to do is find each of these atoms on the periodic table and see what column it's in, starting with carbon. So we're going to look for carbon. You see it's in column 4A. That means it has 4 valence electrons. Next up is nitrogen. We'll find nitrogen. It's right next to carbon. It's in column 5A. That means it has 5 valence electrons. Hydrogen, over on the left side of the periodic table in column 1, it has 1 valence electron. Oxygen, back to the right side, is in column 6A. It has 6 valence electrons. Chlorine, down here, element number 17, has 17 total electrons. 7 of them are valence. And neon, atomic number 10, in column 8A, has 8 valence electrons. So there's that. That should be pretty easy. The Lewis dot symbol is, as I said, it's a picture representation of the valence electrons in an atom. To make a Lewis dot symbol, you start by writing the atomic symbol, and then you draw dots around the atomic symbol, 1 dot for every valence electron. So carbon, with its 4 valence electrons, is going to get 4 dots. The dots are drawn at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock around the symbol of the atom. And they're drawn one single dot in each position before you draw two dots in any position. So nitrogen with 5 valence electrons is going to have 1, 2, 3, 4, 5. And if you just create Lewis dot symbols by going around the clock like that, you'll never mess them up. Hydrogen with 1 valence electron has 1 dot in its Lewis dot symbol. Oxygen with 6 valence electrons has 1, 2, 3, 4, 5, 6 dots. Chlorine with 7 valence electrons has 1, 2, 3, 4, 5, 6, 7. Neon with 8 valence electrons has 1, 2, 3, 4, 5, 6, 7, 8. Sometimes students wonder, is there any particular reason why with nitrogen the pair of dots was put up on top? Would it be wrong if the pair of dots was down here? If you started your dots at 3 o'clock instead of 12 o'clock, would that be a mistake? And no, that's not the case. It doesn't matter where you draw the dot in a Lewis dot symbol. What matters is how many dots you draw, not exactly where they're positioned. So any of these is okay. For oxygen, something like that would be totally okay. It doesn't matter as long as you're showing 6 total, 2 pairs, 2 not pairs, and you're good to go. So that's the Lewis dot symbol. Now, in order to predict how many bonds each of these atoms is going to form, we're going to turn to the Octet Rule. The Octet Rule tells us that atoms, for the most part, want to be surrounded by 8 electrons. No, let me say that differently. Atoms want to have 8 electrons in their valence. Not whatever number Mother Nature gave them. So atoms are going to bond or share electrons with other atoms in order to get themselves up to 8 electrons. There are 2 exceptions to this rule. Well, actually, there are quite a few exceptions to this rule, but in our particular class, there's just 2 exceptions. Hydrogen and helium, they want 2 instead of 8 because they're little. They don't have room for 8. So we are going to use the Lewis dot symbols to help us predict how many bonds each one of these atoms is going to form. Carbon currently has 1, 2, 3, 4 electrons, or naturally has 4 electrons in its valence. Every time that carbon bonds with another atom, it gets 1 more electron. Carbon wants 4 more electrons. 4 plus 4 is 8. So it's going to form 4 bonds so that it can have a total of 8 electrons. And again, this is just about every single bond that an atom creates gives it 1 extra electron. Nitrogen has 5 valence electrons. It wants to have 8, so it's going to form 3 bonds to get itself up to 8. Hydrogen has 1 valence electron. It wants to have 2, so it's going to form 1 bond to get itself up to 2. Oxygen has 6 valence electrons. It wants 8. It needs 2 more electrons, and it's going to form 2 bonds to get those 2 electrons. Chlorine has 7 valence electrons. It wants 8. It's going to form 1 bond. Neon has 8 valence electrons. It wants 8, and that means that it's not going to bond at all. It doesn't want to do anything with any atom at all. So the number of valence electrons plus the number of bonds is always going to add up to 8 for everything except for hydrogen and helium.